All right, so in that last video I was chatting about how we can actually take this Legendre symbol and begin this process of running quadratic reciprocity on it to try to answer this question of whether or not something is a perfect square. So going back to an example that we already know the answer to. So looking at 313 and asking whether or not this thing is a perfect square modulo 2017 boils down to the situation of looking at this 313 Legendre 2017 and asking whether or not that thing is going to return a 1. We know that we can actually compute this by doing some exponentiation and reduction modulo p, but what I want to do here is I want to dive into this quadratic reciprocity so you can see how this Legendre symbol is actually built up and how you can begin to manipulate it. So we're going to take that kind of long approach, but it's going to come full circle a little bit later, so I want us getting comfortable working with the operations that we see now. Again, there's some technicalities of when and how we can use this thing, but it becomes pretty nice. Okay, so a couple things to notice right away is that the number 313 and 2017 are both prime. So I can do this flip-flopping. If the top one would actually be composite, and we'll see that come into play a little bit later, you're going to have to do some factorization and rip those things apart. So if right now we can just begin this flip-flopping as we see fit. The second thing we see is that both of those primes, so 313 and 2017, are going to return a 1 modulo 4. What's nice about that is when we do this flip-flopping of p's and q's, if either p or q are going to return a 1 mod 4, when I flip the p and the q, I don't have to introduce a negative sign, which is nice because I don't want to have to constantly record how many negative signs did I see. What I'm going to see is that I'm going to do one flip and I'm going to create a positive. If I would have the case that both p and q are going to be a 3, so that one should be a p. Sorry about that typo. I'll fix that in the online notes actually. But if I have a p and a q being a 3, we're kind of in the unfortunate situation that when I do the flip, I'm going to have to introduce a negative sign. Okay, so let's go ahead and see how this process is going to unfold. So I have kind of all of them sketched so I don't have to rewrite these as we go, but I'll kind of point and kind of allude to various things as we begin this process. So the first thing is looking at when do I have x squared firing off a 313 modulo 2017. That's kind of our original question is, does that congruence have a solution? So what's going to happen is that I'm going to flip those things using this quadratic reciprocity. So I put the 2017 on top and I put the 313 on the bottom, which is telling me that x squared is now going to fire off a 2, or I'm looking for an x that would satisfy this congruence, modulo 313. So I'm replacing the moduli with that a value if you think about it, in terms of a's and p's. So what happens next is I'm going to take that 2017 and it's going to be reduced down into 139. So in the Legendre symbol operation, we're going to see the following. I'm going to take those things, I'm going to flip-flop the p and the q. So what was downstairs is now upstairs, and upstairs is now downstairs. And then I'm going to take that top part and reduce it modulo 313. So now I'm at this little term. What's nice about this is that those two things, the 313 and the 313 and the 139 are both prime. I still have 313, which is going to return a 1 mod 4, so I can do this quadratic reciprocity one more time. So I can flip those objects around. So that again connects to how can I think about whether or not this thing is going to have a solution. And you can see this kind of natural cascading effect taking shape, is that I start with a large prime, I then get a slightly smaller one, and then I get a smaller one, and at some point in time, I'm going to have a relatively trivial equation to solve, and I'm going to know, yes, that thing does in fact have a solution. So I flip those, putting the 313 up on top, looking at the reduction modulo 139. The 313 then turns into this 35, which is pretty slick. And now I'm at a stage that I have to think a little bit more, because 35 is actually not prime. It's in fact composite. So that thing's actually going to rip apart into a 5 and a 7. What that's going to mean is that my little Legendre symbol is also going to rip apart into 2 pieces. That's using this multiplication process. The idea is that I'm going to get one with a 5 upstairs, and I'm going to get one with a 7 upstairs. And now I'm going to have a branch occurring, is that I now have 2 Legendre symbols multiplied together. So what ends up happening is that I'm going to take this thing on the left, and I'm going to do some arithmetic on it. And then I'm going to take the thing on the right, and I'm going to do some arithmetic on it, and then bring those back and do the multiplication. what we're going to see is that the 5 Legendre 139 is going to return a 1, and the 7 Legendre 139 is also going to return a 1, and the product between those two 1s is a 1, which tells me, yes, 313 is going to be a square modulo 2017. That is, 313 is a quadratic residue modulo 2017. So now let's actually jump and do these two little operations on their own, and then we'll jump back to kind of remind you how this all cleaned up. So taking the 5 Legendre 139, I want to do this flip-flop operation again. So the 5 is for sure a 1 modulo 4, so I can flip the 5 and the 139, putting the 139 upstairs and the 5 down below, and then I can always reduce that top part. So it's the same operation over and over and over and over again. Is I'm going to take the 139, put it up on top, and then reduce it modulo whatever prime I put on the bottom, which is always going to happen. That's kind of the point of all this, is that we're going to begin kind of weaseling our way into a nice little bin where I have smaller and smaller numbers. So if I take 139 and I do the reduction modulo 5, it actually returns a 4. So again, step back and think about, what is that thing actually asking me? This is asking me, is 4 a perfect square modulo 5? And the answer here is yeah, because I know that 2 squared is a 4 in the real number world. Therefore, 2 squared is for sure still going to be a 4 modulo 5. So at that point in time, because 4 is a perfect square, I know that that Legendre symbol is going to return a 1. In general, anytime you have a perfect square up on top, you can split this Legendre symbol into 2, which is going to say something squared, which we know is always going to be a 1 or a negative 1. And if you square it, it's for sure going to turn into a 1. So all this stuff is talking about whether or not something is a square. And in that one, yes, 4 is a square, so it's going to return a 1. If you're actually interested in seeing what's going to happen here, is that if you look at the 4 Legendre 5, it could split into 2 Legendre 5 multiplied by 2 Legendre 5, which becomes 2 Legendre 5 quantity squared. And if you actually look at whether or not 2 is a perfect square mod 5, you're going to see that it's a no. So it's going to be a negative 1. And if you take negative 1 and square it, it's going to turn into a positive 1. So that's where we get our first little bit. That's going to say that 5 Legendre 139 is going to return that number of 1. Officially, that little 2 Legendre 5 at the end, I've actually made use of another version of this quadratic reciprocity. When the prime 5 is small, you can actually spam through them and see whether or not they emerge. That's actually one of these special forms when there's a 2 upstairs. 2 Legendre p is going to be either a plus or a minus 1, depending upon what p looks like modulo 8. So p being a 5, well, 5 is 5 mod 8, so that's where a negative 1 is emerging from technically. Like I said, it doesn't really matter because I was squaring it afterwards, but if you wanted to see why is that a negative 1, it's officially coming from that step. Okay, so let's look at the other half of that one. We're now looking at 7 Legendre 139, and here we're in the unfortunate situation that both 7 and 139 are returning a 3 mod 4. So I'm still allowed to flip these two objects. Unfortunately, when I flip them, I'm going to bring about a negative sign, which is not great, but it's not terrible either. I just have to keep track of extra things. So I'm going to put the 139 upstairs and then do the reduction, which is going to leave me with this little term. At this point in time, we actually could answer this thing because we've been playing with mod 7 quite a bit already, and we know that 6 is not a quadratic residue modulo 7. So what that tells me is that this thing is going to be the negative on the way outside, and because 6 is not a quadratic residue, it's going to fire off another negative 1, which is going to return this positive 1. So you could actually go back and return that second thing is the 1 and terminate it from that. If you wanted to kind of see this thing to completion, what you would have to do afterwards is you'd have to see that 6, and you would again have to factor that thing down because it's composite. So I have a 2 upstairs on the left one, and I'm going to have a 3 upstairs on the other one. So the 2 Legendre 7, that's going to fit into that second case when I have a 2 upstairs. The 7 that emerges on the bottom is obviously going to be congruent to a 7 mod 8. So that thing is going to turn into a plus 1. So that is this fact right here. For the other one, we're going to have to do a little bit of flip-flopping. So I have the 3 Legendre 7. If I flip those ones, you can see that both 3 and 7 are 3 modulo 4. So when I flip them, it emerges as a negative, which is not great, but it's not terrible either. So then if I reduce the 7 mod 3, I emerge with a 4. And at that point in time, again, we know that 4 is a perfect square. So I know that that thing is going to turn into a 1 because 4 is a perfect square mod 3. So that object is going to be my plus 1. I got two little negative signs, which are going to return as a positive 1. So once you get kind of into the weeds or down to the small numbers, you can begin to kind of just think whether or not something actually works. The big process on quadratic reciprocity is taking massive numbers and shrinking them down into these little bits. If you're thinking about actually implementing this or coding this, you need to kind of remind yourself what's going to happen at the very, very last little stages, because you're going to have a few really big kind of reduction stages, and then you got to kind of pick up all the little pieces at the end. And that's kind of the annoying thing when you do it by hand. You're like, I got to take the 6 and write it as a 2 and a 3 and go from there. As I said, you could technically stop here and be like, okay, I know 6 is not a perfect square mod 7, so let's just return that as a negative 1. The negative 1 and the negative is going to return as a positive 1. Okay, let's jump back. Everything is great. We know that 313 is properly going to be a square modulo 2017. So it's a nice little activity on arithmetic. It's also kind of a nice big tree diagram that's going to unfold. Each time you have a factorization stage, you're going to have an additional branch that's going to emerge, and then those little branches may branch into something else afterwards. So as I mentioned, it's kind of a fun little programming activity where you do this flip-flop, flip-flop, flip-flop over and over and over again, where you're constantly just recording all of these little negative signs that are going to emerge. And then at the very end, if you return a positive, you know that you do have a perfect square. If it returns negative, you know that you have a non-perfect square.